Welcome, class, to the fifth lecture of the first week that will cover section 2.2 in our textbooks. This section will focus primarily on factorials, permutations, and combinations. So let's get started. So start off counting in sums, the multiplication principle. Suppose experiment E consists of k stages. Stage 1 can result in any of n1 outcomes. Stage 2 can result in any of n2 outcomes, all the way to stage k, which can result in any of nk outcomes. Then the number of possible outcomes of experiment E is ne, which equals n1 times n2 times ... times nk. To put this in an easier to understand example, suppose Justin owns 4 shirts, 3 pants, 6 pairs of socks, 2 pairs of shoes. How many different ways can he dress himself? Well, NE would equal 4 times 3 times 6 times 2 for the 4 shirts, 3 pants, 6 pairs of socks, and 2 pairs of shoes. Again, 4 times 3 times 6 times 2, which equals 144 ways Justin can dress himself. Now, an easier way to do some of these permutations and combinations is with factorials. So a factorial definition is, you'll see a variable or a number with an exclamation point. That exclamation point represents factorial. So n factorial is equal to 1 times 2 times ... times n for n greater than or equal to 2. 1 factorial is equal to 1, and 0 factorial is equal to 1 as well. An example of a factorial is 5 factorial, which would equal to 1 times 2 times 3 times 4 times 5, which would equal 120. Factorials are used in permutations and combinations. Speaking of permutations, definition. Suppose a set consists of n objects. An arrangement or ordering of the n elements of the set is called a permutation of the n objects. To help further define permutation, the number of permutations of a set of n objects is n factorial. So, for example, set X equal to A, B, C, D. Find the number of permutations of set X. Well, n factorial would equal 4 factorial because A, B, C, D, there are 4 objects in our set. 4 factorial equals 4 times 3 times 2 times 1, which equals 24. So there are 24 permutations of set X. Another example would be to list all of our permutations of set S equal to X, Y, Z. So there are 3 objects in this set. So from above, we know that n would be 3 factorial, which would equal 3 times 2 times 1. So we should expect there to be 6 permutations. Let's see. X, Y, Z, X, Z, Y, Y, X, Z, Y, Z, X, Z, X, Y, and Z, Y, X. I can't think of any other way to permutate X, Y, the letters X, Y, and Z, and according to our formula, we should have 6, and that is what we have. So, looks good. A couple notes about permutations. Note 1. For permutations, the order in which we list the elements is important, i.g., permutation XYZ is distinct from permutation ZYX. Note 2. A permutation contains no repeated elements from the set. A good way to think about permutations is running a race. Say there are 3 people running a race. It is very different for a person who comes in first and the person who comes in third. The order of who crosses that finish line matters. That's the idea behind permutations. Another example. Suppose it is allowable to repeat elements of set S equal to x, y, z. How many distinct 3-character sequences are there? Well, since we can repeat, that means there are 3 options for first place, 3 options for second, and 3 for third. So 3 times 3 times 3, which equals 3 to the third, which equals 27. We will be honest, we probably won't see this situation happen too often. Definition. Suppose that from, oops, scrolled up too far. Suppose from a set of n objects, we select R objects. Each such sequence is called a permutation of n objects taken R at a time, denoted as n, lowercase n, capital P, lowercase r. You'll often hear me refer to this as n permutate R. Definition. The number of permutations of n objects chosen R at a time is n permutate R equals n times n minus 1 times n minus 2 times ... times n minus r plus 1. For example, the number of ways to choose a chairman and a vice chairman from a committee consisting of 5 members is 5 permutate 2, which would equal 5 times 4, which would equal 20. A way to think about this using my previous example of running a race, there may be 10 people running the race, but in general, we only care about first, second, and third place, so that would be a 10 permutate 3, which would equal 10 times 9 times 8. A second example would be, for committee members are Al, Bob, Cindy, Darla, and Ed. List all possible selections of chair and vice chair. So that would be a list of all possible combinations of our 2 positions. And again, since chair and vice chair are 2 distinct things, saying Al and Bob and Al are 2 different things. So note, a way to calculate this would be to n permutate r can also be written using the factorial, equal to n factorial divided by n minus r factorial. That brings us to the end of our permutation section. Now we're going to move on to the combination section. I can tell you from experience, we'll be doing more combinations in this course than permutations. So combinations. Definition. Suppose set S consists of n distinct objects. An unordered subset consisting of R of the n objects is called a combination of n objects taken R at a time. So, for example, a committee consists of Al, Bob, Cindy, Darla, and Ed. 2 members will be selected to attend a conference in Hawaii. How many distinct pairs can be chosen? Note, unlike in permutations, order of selection is unimportant for combinations. It doesn't matter if Al is chosen first or Bob is chosen first. Both are going to Hawaii and will presumably stay on the same flight and having the same accommodations, so order is unimportant. Therefore, the following pairs may be selected: AB, AC, BC, AD, BD, CD, AE, BE, CE, and DE. There are 10 distinct combinations. Definition. The number of combinations of n objects chosen R at a time is denoted as lowercase n, capital C, lowercase r. You will hear me refer to this as n choose R. And it is calculated by n choose R equals, and this is another notation that you should be familiar with and will be used later in this course, where we will have our n over our r in parentheses. This is another way to denote combinations and is still n choose r, which is equivalent to n factorial divided by r factorial times n minus r factorial. So going back to our above example, with Al, Bob, Cindy, Darla, and Ed, where we are selecting 2 members of our total of 5 committee members, we would do 5 choose 2, which would equal 5 factorial divided by 2 factorial times 5 minus 2 factorial, which would be equivalent to 5 factorial divided by 2 factorial times 3 factorial, which we would further simplify to 10. And if we go back to our example, we can see that we had exactly 10 distinct combinations. So that checks out. So our final example in this section asks how many 5-person starting teams can be selected from a basketball team consisting of 12 persons, disregarding position. This would be 12 choose 5. Plugging into our formula, 12 factorial divided by 5 factorial times 12 minus 5 factorial would simplify to 12 factorial divided by 5 factorial times 7 factorial, which we would further simplify to equal 11 times 9 times 8, which we would equal to 792 combinations. Wow, that's a lot. And that brings us to the end of section 2.2. Have a good night, everybody.